Hello everyone, welcome to the second video of our lecture 3, cryptography and hash. As you remember, we talked about basics of cryptography in the previous video. Today I'm going to continue that, and hopefully we can see the first commercialized encryption algorithm, which was DS encryption algorithm. Okay, I'm going to, like I said, I'm going to talk about first uh, one or two kind of classical encryption algorithms. One of them is called Caesar cipher or Schiff cipher. The reason they call it Caesar because this is somehow assigned to Julius Caesar, the Roman general. They said that this was first used by that general when he wanted to communicate with his officers and soldiers. And the way it works is very easy. It says, okay, you have a text, for example, you want to encrypt that text. Of course, you want to use a set of symbols or characters. Let's assume that this letters or characters that you are going to use are only lowercase English alphabet letters, 26 of them. And the way it works, it says that you consider a number. Here in our example, let's consider 4. And every character is going to be mapped to its 4 later characters. So A is going to be mapped into, this is, let's say, for example, 1, 2, 3, 4, 5. So 4 letter later after A is going to, which is E, A is going to be mapped to E. So in this type of cipher or encryption, whenever you want to use A, you put E instead. So here is the example. We have the plain text is hello, and we are going to encrypt hello. We come here, H is here, 4 letter after H is 1, 2, 3, 4. So H is going to be mapped to L. So instead of H, I put L. E is here, and this list basically shows the encryption that one by one, that A should be mapped to E, B should be mapped to F, and so on. And okay, E here should be mapped to I. If we go one by one, L should be mapped to P. And so we have LIPP, and finally O should be mapped to S. So instead of hello, we get LIPPS, which is of course not easy for someone who doesn't know this rule to understand. So we formulate it this way. We say that, okay, we consider an index or number for every letter, starting from A, which is 0, all the way to Z, which is 25. And we say E of, or encryption of, the character M and the coding with the key K. Here, K is the code. Sorry, K is the key of this encryption, which in our example, we assume K is 4, but it might be anything. For the K of 4, let's say continue, for example, if we wanna encrypt, for example, if we wanna encrypt E of 4 and letter A, it goes and looks at the index of A. A is 0, add 4 to that, makes it 4, jumps to cell 4 and brings kind of returns that letter. So encryption of A and 4 is going to be E. And the way it works is based on this formula. It says encryption of character M and the key K is going to be the content or the value of the M plus Kth element in this array. Of course, you take the mode 26 because, for example, for Y, let's say Y, or for Z, for example, which is at the last cell, it's going to be, the kind of Z should be mapped to the 4 letter later. So we say 1 after Z is A, P is the second, C is the third, and D is the fourth. So Z will be mapped to D. That's why you see this mode 26 here. It is here to help us to kind of rotate or wrap around this list. And if we apply it for our example to the to this list with a key of 4, this is the original kind of set of alphabets, and this is the encrypted one, or the mapping. And if we look at them by eye, you see there is some type of shift. That's why people also call it shift cipher. The key space here is very small. If you are using a list of 26 letters, your key is maximum 26, because the key or parameter k should be anything between 0 all the way up to 25. If, for example, you consider key of 27, key 27 will be working something like 1. It is like 1. Yeah, it rotates A to the 27th letter after that, which is going to be B. Because you go one direction, this is 26 and 27 is here. So A is going to be, again, mapped to B. So K of 27, what it is doing is similar, it's doing something similar to K of 1. So we don't have more than 26K. So it is clear that the encryption is pretty simple, but at the same time, it's not that kind of strong. This is the first encryption, or the first classical cipher. The second one that I want to also point to this is called shift cipher. I'm sorry. Yeah, it is called. Okay, let me first give you this example. Before going to the second one, how can we break the shift cipher? Like I said, since the key space is very small, we can do it very easily. Here is one example. We have this text, which is basically the cipher text, or the encrypted text. And we are going to break this using brute force attack. So what we normally do, what the attacker normally does, is that attacker comes and apply different keys. Attacker assumes key of 1, key of 2, and all the way to key 25. Okay, and for every key, if you decrypt this ciphertext, you'll get some plain text. And we just need to look at the different plain text that we get and see which one makes sense. Okay, this is the decrypted version of the ciphertext with the key 1. It is not a meaningful sentence. This is not a meaningful sentence either. The only case that you see we got something meaningful is here, when key of 3 was used. It says meet me after the toga party, which is something meaningful. So it is clear that the right key which is used for this encryption was 3, and once we use the key 3 or k of 3, we could clearly break the encryption, and we could get the plain text out of it. So this again shows that it's not a pretty strong cipher or encryption algorithm, but I just wanted to bring it as a kind of a history of encryption. The second cipher, which is again classical cipher or an encryption algorithm that I'm going to talk about, is called substitution cipher. It is something similar to the Caesar cipher, but it says that here is your example. Here's your kind of original alphabet that you wanted to use, and you want to make a mapping to the other letters of the same alphabet or set of characters. You don't need to shift them. You don't need to rotate them. You can do any type of mapping. For example, you have 4 objects. Let's say object 1, 2, 3, 4. In the Caesar cipher, you need to map them one by one. For example, like this, using some shift. So if 2 goes to this, 3 should definitely go to this. But here it says no. You can map them any way. 1 can go here, 2 can go here, 3 can be mapped to this, and 4 can be mapped to this. There is no limitations. There is no requirement that they should be mapped one after each other. Here's one example. A is mapped to F, B is mapped to M, and there is no regulation. There is no kind of mathematical rule based on the mapping that we just came up with something. In terms of key space for this specific example, or let's say for a set that we have 26 symbols or characters, the key space seems to be very big because for the first one, let's say we are talking about 26 letters or 26 characters. First one has the option to be connected to or to be mapped to 26 different symbols. The second one, only one of these 26 has been used and the rest of them can be used. So 25 options are available. For the third one, 24 option is available and so on. If you do that, you'll get this number, which is a pretty big number. The key space seems to be very big, 26 factorial, but there is one important thing that would be helping attackers to easily break this type of cipher or encryption. That's the clue that we get from the English language. Structures and guidances that we can get from the English language writing, it would be helpful. And here I have an example that shows how we can break the substitution cipher easily. Assume that this is the ciphertext and we are going to break into this. We don't have the key, of course. We don't know the mapping. We don't know, this is basically the key here. This mapping here is the key. If someone wants to decrypt this encrypted text or ciphertext legibly, we should provide them the key, and based on the key, they can be able to easily decrypt the ciphertext and then get access to the plain text. But this is a ciphertext, and we are attacker. We don't have access to key. We just want to use the structures of the English language in order to break into this algorithm. So for doing that, we look at the frequency of letters in the English language. This is from some studies, and it shows that, of course, we understand this. We all agree on this point that letters are not being used with the same frequency in the English language. Some letters are being used. For example, E is the most frequently used letter in English, and maybe Z is the least one. Yeah. Okay, this would be helpful to us. We are going to use this information in order to kind of break into that algorithm. And also, when it comes to one-letter words, we don't have much one-letter words. So when we see, for example, this T, it applies me that it should be either I or A, or that's probably what it is. Or something again for two-letter words. In two-letter words, we don't have many possibilities. They're limited, and so that would be helping us. So let's look at this example using that frequency of letters. And the first thing that we do, of course, is that we come and we look at the frequency of different letters in the ciphertext, in the encrypted text. So if we do it, we get something like this, that, okay, here in this ciphertext, A has repeated 3 times, B has repeated 3 times, and so on. And the maximum thing that we see is X. X has repeated 13 times, and this implies that X should be E. X has used as a representative of E, and which means that X here is the main, or is E. X in the ciphertext is E in the plain text, or we don't know the whole key, but a part of that key is this, that X is assigned to E. Okay, we continue this and we assume that X's are E. Okay, we assume that x's are E and we put E instead of each X. Here is a part of the plain text that we are trying to extract. The next thing, we can look at some of the two-letter words. For example, we have OX here. That a part of that is extracted already. So this should be an OX that ends with E should be either B. This should be, for example, B in English, or he, or me, or we, any of these. But again, the frequency of or the number of times that O here, which is, we are going to break it, how many times it's repeated is also going to be helpful. If we look, O has repeated in our text 8 times, which is not that low, it's pretty good. So 8 O should be something which is also repeated many times, which repeats many times in a kind of basic English. Again, let's look at this chart. Okay, here we talked about the first thing is E, and then out of B, H, V, and the last one, what was the last one? And me, yeah. We look at B, B is this, H is this, W is here, and M is here. Okay, H has repeated the maximum. So since that letter that we are talking about is also repeated quite a few times, so we assume that here this O stands for H. So yes, we guess that O stands for H. Let's consider that and put H instead of O, so our kind of plain text gets updated. We understand some more letters, and if we continue this with the same kind of structure, here, for example, is another word that most of it we know. We have 3 letters of that kind of decrypted, and only 2 letters are left. So this should be 3 or these or where, considering that, for example, we don't have any question mark or single thing at the end of the thing. We assume that it is T, and then we go forward. And then after a few while, you can look at the details of this example. It's all about finding some words and trying to break that specific word. And you see that we can, let me go forward, the same thing. We can break the encryption, and we can decipher or decrypt the text, which is very good and very kind of interesting. Even without knowing the key, although the key space is very big, we said that it's going to be 26 factorial, but we could break the key, and here is we could break the algorithm, and here is a plain text. There are 2 times in a man's life, blah, blah. And it came out of the only kind of way we could do it is that we looked at the characters, frequency of repetition of characters, and we get help from the 1 character words and 2 character words, and we use the kind of the English language clues in order to help us to break into this encryption, and we could do that. Okay, these are 2 classical encryption algorithms that I just wanted to mention to show you that a simple mapping like shift or change of the letters or change of characters is not enough. Although sometimes the key space is big, but the meaningful relations, they will be helpful. They can help the attacker in order to break the encryption. So the commercial encryption algorithms, they of course may use some type of substitution. They substitute the characters, one character with something else, but that shouldn't be all. There should be other things on top of the encryption as well. Okay. Now we are very close to start the first commercial encryption and see the details of that. But before that, I need to give you a few more kind of introduction, or maybe define some terminologies for you, and then we get to the first one. We have two types of encryptions, which are called block cipher or block encryptions. They don't say block encryption, they say block cipher and stream cipher, but it means encryption or cryptographic algorithms that work with a block of data, or they work with a stream of data. In a block cipher, which is showed here, this is the block cipher. For encrypting the information, for encrypting the data, you're gonna break the data into some piece of information. For example, 128 bits. Every block of the data is 128 bits, or is 64 bits, or whatever. That's called block of data. That block of data is going to be used as an element that which is going to be encrypted at a time. And of course, the encryption or the cipher works on these, performs some processing, and after a while, of course, that processing is a function of key. It gives you a cipher block, or a block of ciphertext, which is the encrypted version of the plain text inputted to that. The key here, the key K here, might be used for multiple blocks or might be updated. You may use one key for multiple blocks, or you may change it. That's kind of based on that will be determined based on the details of the algorithm. Okay. In contrast, we have a stream cipher at which data comes in a stream of data. For example, every cycle or every second, 1 byte of data comes, or 1 kilobyte of data comes. And the stream cipher or stream encryptor is supposed to receive that data plus the key, and it just encrypted on the way or on the fly. So elements appear, elements or plain text kind of arrives continuously, and the cipher produces the ciphertext again continuously over time. And you may wonder how is kind of stream cipher is beneficial with respect to block cipher. The main thing for stream cipher is that they are good for helping the speed of the encryption. Of course, if you can do the encryption on every byte instead of 128 or something, you can do it over time. And there would be a kind of situation that we call it pipeline. And in the pipeline, you can kind of get some type of parallelism in the encryption. And that will be helping in terms of speed, our encryption process. In stream ciphers, they mostly work with random numbers or pseudo-random numbers in order to maximize the kind of the strength of encryption, which is somehow tricky because at the end of the day, this encryption is going to be run on a processor or somewhere, and generating true randoms on processors or on hardware is not easy. That's why sometimes we say pseudo-random, not pure random. Okay, if we wanna kind of update our classification regarding cryptographic algorithms, we said that we have asymmetric and symmetric encryptions. These are all encryptions or cryptographic algorithms. We have asymmetric and symmetric. In symmetric, we have two, block cipher and stream cipher. Now I'm going to start and talk about a few examples. So examples that we are talking about them, they fall both under the category of block cipher of symmetric. Later in this lecture, we'll be talking about one asymmetric encryption algorithm as well. Here is the RSA, and that's it. So we'll be talking about 1, 2, and 3 of them. Okay, this is the last series of features that I'm going to introduce regarding block cipher encryptors or block cipher encryption algorithms. What are the properties that we expect or they are desired for us when we use a block cipher? There are two important properties that we need to see when we apply a block cipher encryption. The first one is called diffusion. Diffusion means that the process of the encryption should be showing some type of spreading effect, which means that every bit of the plain text or key should be spreaded as widely as possible over the ciphertext. So to kind of explain it maybe in a different way, I can talk about the effect that we expect to come out of this property, diffusion property. That effect is called avalanche effect. And the avalanche effect, I'll show the avalanche effect to you in some real examples. But what it says is that it says that changing one bit of the plain text, there we go. If we change only one bit of the plain text, we should see more than half a bit of the ciphertext be changed. So this is our plain text or the data that we want to encrypt. We apply something, we get something. So this is, let's say, plain text number 1, and this is ciphertext number 1. If I change the plain text number 1 to plain text number 2, and plain text number 2 has only one bit different than plain text number 1, the cipher 2 and cipher 1, they should have more than 50% different bits. This is a property of diffusion. It says that changing one bit of the plain text should show more than 50% changes at the cipher. And the reason we want this property to be held is that if we don't have such property, it would be very easy for the attacker to find some relations between input and output. It would be giving the attacker some clue. Remember about the substitution cipher that we just talked about it. I showed you that we have the key space of 26 factorial, which is pretty big. It's very big and good. But because of that clue and that relation that we can find in English language, we could break the encryption very easily. Why? Because there is no diffusion there. If you change one bit in the input text, or if you change one letter, what is going to be changed at the output or the ciphertext? Only one letter. For example, O becomes something as S. And which means that not all the we cannot claim that more than 0.5% of characters that we have in the plain text, in the ciphertext, are going to be changed. This is what we expect from the diffusion. And when we say kind of standard encryption, they should show, or everybody who has presented the encryption, they should show that their encryption or the cryptographic algorithm, they fulfill this property. And the second one, the second property that we like to see is called confusion. And it says that the relation between the key and ciphertext bit should be complicated. Or another way, if we want to put it statistically, we can say that ciphertext and plain text should be appear to be statistically independent, which again means that I, as an attacker, shouldn't be able to find clues between, shouldn't be able to kind of apply some input and extract some relation between input and output, between plain text and ciphertext. So this is the second property that we want to have in the encryption algorithms. Okay, the last thing, which is not 100% required, but it's a property that we should be aware of, is the efficiency. When we say efficiency of encryption algorithms, here we are talking about the speed and the how that encryption algorithm is easy for implementation. When we say speed, that's important for us because the rate of encryption and decryption or the number of encryption and decryption that we can do per second is important to us. Of course, if everything is similar between two encryptions, you have encryption 1 and encryption 2. The first one let's say on a given processor, it gives you, let's say, 1 million encryption per second. The second one gives you 5 million encryptions per second, which means that its computation is basically 5 times less. So if everything is similar in terms of size of key, hardware required, blah, blah, of course you go with encryption number 2. So the rate of encryption and decryption is also important for us and is a parameter, is a quantitative parameter representing the efficiency of that encryption algorithm. Also, the easiness for implementation matters. We care about how easy is implementing one encryption algorithm. Some encryption algorithms, they might be difficult for implementation. And like I explained in the previous video, encryption algorithms, some of them might be susceptible, might be vulnerable to side channel leakage. On the paper, the encryption algorithm is okay, everything's okay, key is big enough, blah, blah. But for example, the power leakage of the chip might be used in order to break the algorithm. So this is the third property, which is not mandatory, but it's very important and it makes a big difference when we are talking about cryptographic algorithms. Okay. Now I'm going to show you a high-level block diagram of most of block ciphers. Of course, now we are talking about block ciphers, which means that a block of data comes. It might be any size. Let, for example, say assume 128 bits of data comes, and a block of encrypted data or cipher goes out, which might be less or more. Let again here assume 128, but it might be less or more. It's not required for encryption algorithms to encrypt 128 to 128. Anyway, this is the high level or abstract version of block ciphers. It is called iterative structure because what you do is that you do some initial processing for the plain text. That initial processing might be anything we'll see, and then you have some finalizing processing. And in between, you have multiple rounds of encryption. Round 1, round 2, round 3, and so on. And of course, for each round, you apply some key. Key 1, key 2, up to key R. And these subkeys, these are called subkeys. Subkey, or sometimes we also call them round key. Subkeys or round keys are going to be extracted from the main key. So when you want to encrypt your text, you just apply one key, not more. But that key is going to be used in a module inside the encryption in order to extract round keys, in order to find round keys or subkeys. And the subkeys are going to be used for each subkey is going to be used for each round, because you don't want to use the same key. Otherwise, it's not gonna be helpful. It doesn't fulfill that both confusion and diffusion. It doesn't fulfill them. So that's why we extract sub round keys out of the main key, and that way we can get most out of the confusion and diffusion. Okay, we are going to go ahead and talk about the first encryption that we want to review in this lecture. Is called Data Encryption Standard, or DES. It is being developed based on one algorithm which is designed by this person, Horst Feistel. He designed the algorithms of Lucifer and at IBM in 70s, and the length of the key was 128, and the length of block was 128. In 1973, National Bureau of Standards asked for some block cipher protocols or proposals, and IBM submitted multiple variants or versions of this algorithm. And in 1976, they have adopted it. They have kind of used it. And of course, after applying some changes, the key length was changed to 56 bits and the block change was 64. We'll see the details. And eventually, this is a kind of interesting part. Having 56 bits of the key, it gives me 2 to the power of 56 bit key space, which is a pretty big number. But in 1997, people could break DES using exhaustive search or using brute force attack. So it means that 2 to the power of 56 is no longer enough. It has not been long enough, basically since 1997, which is something about 24 years ago. Okay, here are the high-level block diagram of the DES. It's pretty similar to that basic or abstract model that I just showed you. It has multiple blocks or multiple steps. We have something here which is called initial permutation. The keywords that you see here, they're all following the standards, and if you use these keywords on the internet, you can find many resources. For example, how the initial permutation in DES encryption algorithm is going to be done. You can see videos, you can find many documentations about it because this has been used for a long time. So it has an initial permutation step that we will be talking about it, what it's going to do, and then a final permutation step. And there are 16 rounds between the initial permutation and final permutation. And each of those 15 rounds is going to work with a round key with the length of 48 bits. So it takes a key, 48 bits, performs the first round of the encryption. It takes another key, another round key, again 48 bits, performs the second round, and all the way it takes another 48 bits and conducts the last round of encryption. But these 48-bit keys, they're coming out from a 64-bit master key. They're being extracted from a 64-bit master key that we will be showing how that happens. Okay, the initial permutation follows something like this. Of course, we are talking about a block of 64-bit data. Look here, we are talking about this is our this is basically our plain text. Oh, sorry, it's not very good. Which is 64 bits. And this bit is called bit number 1, and this is bit number 64. So if you're if you're used to binary numbers and hex numbers in computer domain, you know that we normally call them this way. We normally count them this way. We say that this is bit 0, bit 1, and this is bit 63, sorry. Because this carries the value of 2 to the power of 0, this carries the value of 2 to the power of 1, and all the way this carries the value of 2 to the power of 63. But this is not the way we look at them here. The reason is here we are not looking at the value of that number. The plain text for us is just a string of binary numbers, a string of 0 and 1. That's how we see that. That's why we count them from this side. We say that this is bit number 1 and this is bit number 64. So we continue this counting or this labeling strategy from all of the other encryptions and all of these slides that we have in this lecture. Anyway, this is our plain text which is going to be applied, and in the initial permutation, this is what we are going to do. Bit number 1 will be applied to it goes to bit number 40. Bit number 2, it goes to bit number 8. Bit number, for example, 58, it will be applied to bit number 1. This table shows all the permutation, the initial permutation. It is just shuffling the bits of the plain text. 1 goes to 40, 2 goes to 8, 3 goes to 48, 4 goes to 16, and so on. And so on. This is called initial permutation. The reason for having this, it is something like substitution cipher. If you remember, we talked about it, that the substitution cipher just changes one letter to another letter. It somehow is like that. And of course, it's not adding, it's not enough for a complete encryption algorithm, but it's a part of that. So it follows this table in order to apply the initial permutation. After the plain text is permutated, after this step is being done, now the data which is 64 is going to be applied to the encryption. The first round starts. And the rounds, each round works like this. See, this is a 64-bit of our data. If we assume that this is round 1, this is just the 64-bit data which comes out of the initial permutation. So the initial permutation is done, and we get something which is again 64-bit. The algorithm breaks that data into 2 parts. 32 bits at the left, 32 bits at right. So this is called L1 and R1. Means that the left side of that 64-bit data, or 32 bits at the left side, 32 bits at the right side. If you look, this architecture basically shows what is going to be done. The right side, R1, is going to be applied directly without any change. It goes to the next round. it means that the right side 32 bits of data, it doesn't experience any change or any processing, any type of encryption. It just being applied to the next round. But the left side, it comes here and it's being XORed with something that comes from right side. So here we have a few things that we need to consider. First, this is the XOR operation. This is a logical XOR operation. Logical XOR operation, for those of you that you might forget that, I'll just put it here. I'm talking about one single bit. If you have one single bit of 0 and you are going to XOR it with 0, it gives you 0. XOR of 1 and 1 also is 0. 0 and 1, when you XOR them, you'll get 1. 1 and 0, when you XOR them, you'll get 1. So basically, when you XOR 2 bits, you'll get 1 at the output if they are different, if the input bits are not similar. If both of them are 0, or if both of them are 1, you'll get 0 at the output of the 0. And here, when we say XOR here, it means that we are, in fact, we have 32 bits come out of this function and 32 bits that comes from Li or L1, and we XOR them one by one. These two will be XORed. These two will be XORed. These two will be XORed, and so on. So we are XORing bit by bit. Okay, L1, here we are assuming that we are talking about the first round. The L1 will be XORed with something that comes from R1. And R1 here is going to be applied to a function. This function is very important. We call it encryption function. This function takes R1 and takes the round key, 48 bits, 32 bits. It takes both of them, and it gives us an output which is 32 bits. And then we get out, we take that output, we XOR it with L1, and what we get will be used as the R for the second round. So this should be R2, and this goes to L2. And again, the same round. Now we can assume that this is just turns back here. Again, the right side, which is R2, now just goes to L3, and then L2, which is here, it comes here and it's being XORed with a function of R2. And then what it produces will be R3. Okay, here is the encryption process, and here is the decryption process, which is reverse of the decryption is, of course, reverse of the encryption. But what I'm going to now talk about is this function. This function seems to be very important because, like you see here, R1 is just moved to L2 without any change, and L1 is being XORed with the output of this function. So this function is very important. The encryption function that we are going to talk about, yeah, this is the same thing. Yeah, this is the encryption function, or DS function. It's being called encryption function or DS function. This is the function. It takes 32 bit. Basically, what it is, the input here is RI, the rights of the right 32 bits of our data in any round. It comes, and then one function is being applied on that, which is called expansion, and we make that 32-bit 48 bits. So this is the first step. We'll be talking about the details of this. And then we get the key, which is 48, and again we apply the XOR. So 48 bits is going to be XORed with the key of that round, bit by bit. Again, this XOR, you see one XOR symbol here, but it means that applying the XOR on corresponding bits. So bit 1 of this line is going to be applied, is going to be XORed by bit 1 of here, bit 2, bit 2, bit 3, bit 3. So basically this is 48 XORs, but we don't show all of them, we just show one. And then the second step or the second phase of this ES function is something which is called S box or substitution box. We talk about the substitution box. There are 8 different substitution tables that we look at them, and for every 6 bits, we get a 4 bits. So this substitute the data and also at the same time compress the data. It makes a 48 bits, again 32 bits. And then the third step is called straight debox. Again, we apply some function on that, and we get the final 32 bit, and it goes to the next round. So this is now is going to be stored here as Ri plus 1. Sorry, this is going to be XORed here with something that comes from Li, and it's going to be now here saved as Ri plus 1. Okay, now I'm going to talk about each of these 3 steps. Probably we cannot finish all of them today. What I will be doing, I try to finish the expansion debox and then maybe to some extent Xbox. And then we continue in the next recording. Okay, this is the expansion debox. Like I mentioned here, we apply 32 bits of data, and this expansion debox makes it 48 bits. So this is some expansion. You can do it this way. This is what they have suggested in the DS function. They say, okay, this is your let's say bit 1, bit 2, bit 3, bit 4, and all the way this is your bit 32. Yeah. Bit 1 goes to, and this is and altogether this is 32 bits. And this is the output, bit number 1, bit number 2, bit number 3, all the way to bit number 48. So bit 1 of the data goes to bit 2 of the output. Bit 2 goes to bit 3. Bit 3 goes to bit 4. Bit 1 of the output data of the expanded data looks at bit 32. So this bit 32 is used in 2 positions, in position 47 and also in position 1 is repeated to be here. So in fact, bit number 32 will be used to fill 2 different places. The first one is bit number 1 at the output and bit number 47. So this is the expansion. We are using 1 bit to fill 2 positions. And this is the structure. Bit number 4 is used to fill position number 5 plus position number 7. Again, bit number 4, look at here. It is applied to 2 positions, position number 5 plus position number 7. Bit number 5 is applied here to position 6 and position 8, and so on. This table shows how it works. If we kind of number our bits of the data from bit number 1 to bit number 32, if you, as I mentioned here, bit number 1 is going to be appeared at the position 2 of the output. So this is what you see. Second bit, this is the first bit of the output, second bit of the output, third bit, and so on. The second bit of the output should be filled by bit 1 of the input. The third bit should be filled by bit number 2 of the input, and so on. Of course, some bits, for example, you see here bit number 1 of the input is used both for output 2 and output 48. That's the expansion. Or because like I said, bit number 1 of the input goes to both number 2 of the output and number 48 of the output. That's why you see here number 1 here at the position 2 by bit 2 of word 1 and also bit 6 of the word 8. I called each of these a word. This is word 1, word 2, all the way to word 6. And this is the expansion debox, like I said. And you see that it expands the 32-bit data to a 48-bit one. The next thing is called SBox. SBoxes, like I said, we have in DES, we have 8 different Xboxes, or X stands for substitution. They do the substitution. And what an Xbox is, here is one Xbox, for example, Xbox number 1. If you come here, you somehow point to this cell, you'll get a 4-bit data. You'll get a 4-bit data. Every cell contains a 4-bit data. If you look, the content of the cells maximum are 15. And you don't see anything bigger than 15. And 15 in decimal, the numbers are written in decimal, but we eventually look at them as a binary number. 15 in binary it is 4 ones in binary, which is kind of base 2, and it is 4 bits. So in a 4-bit space, we can have all zeros all the way to all 1. All 0 kind of represent 0, and all 1 represent 15. So that's why we say SBoxes return a 4-bit data. And we apply a 6-bit a portion of data, which is 6-bit to SBox, and we get 4-bit out of that. That's why here we say that if you look at this function again, we say that 48 bits of data will be applied to XBox, and after that we get a 32-bit, because SBoxes work like this. For every substitution, what they require is they require a 6-bit in order to point to some cell, and then out of them you get a 4-bit out of that cell. And that way, for every 6-bit, you reduce 2-bit. So out of that 48, it makes your 48 32. Okay, each XBox, like I said, is a table of 4x16, and each cell contains a 4-bit data stored. SBox is the nonlinear portion of the encryption algorithms, which means that it's not reversible. No one can kind of undo it. But that's not the case for other functions. For example, here, I'm going to go to the details of the SBox in the next video, next week. But the last thing that I'm going to say is that if you look at these steps here in the DES, every step is reversible permutation. If I know the permutation rule based on the Kirchhoff's rule, we said everything should be open. So everybody knows this. Everybody knows this table, this permutation table. So if you tell me that what's the output here at the end of the permutation, I can say what was the input, because I also know this table. I'm an attacker, I know this table. So this is reversible. I can reverse it. I can reverse this part. I can reverse the expansion. This is also reversible. If you tell me what is the output, I can find the input as well. But the SBoxes are the only part which are not reversible. Okay, I think we can stop here. I'll be continuing from here and talking about SBoxes in the next recording. Thank you for making today, and please use SBoxes like these as the attendance code for today's class. Have a good day.